Example 4 says if cotangent of alpha is equal to 3 halves and alpha is in quadrant 3, find the other trig function values. So this is not going to be to scale, but we have our right triangle here. And because it's in quadrant 3, we know that both the x and the y coordinate for our terminal points are going to be negative. Now, cotangent of alpha is equal to cosine of alpha over sine of alpha. So if we think about this as a right triangle, the x coordinate is going to be -3 and the y coordinate is going to be -2. Now, to kind of reiterate something I said in a previous outline, triangle side lengths are not negative, but this is on the xy plane, and so we are thinking about the coordinates. Another thing to keep in mind is that the way that I've drawn this particular right triangle is not on the unit circle, and the way that I can tell that is because if I use the Pythagorean theorem to find the length of the hypotenuse, we're about to see that it's not going to be equal to 1. So one of the side lengths is equal to 3, and so if we square that, and the other side length is equal to 2, and we square that, we want to see the length of the radius, or maybe I'll call it c squared for the hypotenuse. So 9 plus 4 is equal to c squared. That is 13, so c ends up equaling the square root of 13. So this length here is the square root of 13. So to reiterate, this is not on the unit circle since our radius or the length of the hypotenuse is not equal to 1. We could scale it down so it is on the unit circle by dividing all 3 side lengths by the square root of 13, but I think it's just easier to work with it like we have it in this scenario. So we already have cotangent of alpha equaling 3 halves. It's really simple from this using the reciprocal identity. We know that tangent of alpha is just going to equal the reciprocal of 3 halves, which is 2/3. So that one's nice to get out of the way. Let's do sine of alpha next. So sine of alpha is going to be opposite over adjacent. And so this is the angle that we're looking at here. So the opposite would be this one, and the adjacent would be the -3, and then the hypotenuse would be the square root of 13. And I made a mistake here. That should be opposite over hypotenuse since it's so katoa. So sine of alpha is equal to opposite over the hypotenuse. So that's going to be -2 over the square root of 13. And we want to rationalize that. So I'll multiply that by the square root of 13 over the square root of 13. So that's going to end up equaling -2 root 13 over 13. So let me just box these so I make sure that I get all of them. Okay, if we have sine of alpha using the reciprocal identity, we can get cosecant of alpha by taking the reciprocal. And what's nice is earlier I had it in this form, and I can just swap the numerator and the denominator in that thing I just highlighted, and we find that cosecant is equal to negative square root of 13 over 2. And then cosine of alpha is going to equal adjacent over hypotenuse, which will be -3 over the square root of 13. And I want to rationalize that. And so that's going to end up giving us cosine of alpha is equal to -3 root 13 over 13. And then the last one that we are missing is secant of alpha, and that is the reciprocal of cosine. And I'm going to take the reciprocal of that thing that I've just highlighted, and that's going to be negative square root of 13 over 3. And so here we have found all 6 of the trigonometric values of this angle alpha. Now, one thing that I want to point out is all of these values that we've found here, these are not angles. They are ratios of side lengths. So I'll just write this out. These highlighted values are not angles. So students will sometimes get confused about that. The thing that is the angle is the alpha. Alpha is an angle. We just don't know what it is. In a later section in the quarter, we'll be able to solve for alpha, but we don't have the tools to do that right now at this point. So we do know alpha is an angle and it's in quadrant 3. We just don't quite know exactly what it is yet. The highlighted yellow values are not angles. They are ratios of lengths. So keep that in mind. Now we're going to talk about area of triangles. Pause here to see if you can remember the formula for the area of a triangle. Suppose we know the length of two sides and the angle that they make. How might you express the height with respect to the given information? So if you remember from geometry, the area of a triangle is equal to 1/2 the base times the height. However, in this example here, let's say we know A, we know B, and we know theta, but we don't know H. Luckily, we have trigonometry now under our tool belts. So the area of this triangle is going to equal 1/2 B times, what's another way that we can write H? Well, if I'm using angle theta as my reference here, then B is going to be my adjacent side length, and A is going to be my hypotenuse, and then H, if I think about this right triangle here, the H value would be the opposite length. And I actually don't need the adjacent value because B is actually shortened, so it actually wouldn't be B since our new right triangle has a bottom length of that, so let's ignore B. But however, I can make a trigonometric statement using theta, the opposite side length, and the hypotenuse. And so the statement I can make, and I'll make it off to the side here, is that sine of theta is equal to the opposite, which I'll call h, over a. And if I solve this equation for h, which is the height, if I multiply both sides by a, we end up getting that the height is equal to a times sine of theta. So I'm going to plug that in here. The height, and I'm going to substitute it, is equal to a times sine of theta. And if I kind of move that around, basically multiplication is commutative, which allows me to reorder. We get that the area of the triangle is equal to 1/2 a times b times sine of theta. And so look at that. That's the same equation that we have down below. So the area A of a triangle with angle theta and with side lengths of A and B respectively as initial and terminal rays of the angle can be given by this equation. And that is the one that I just derived for us here. Example 5 says, find the area of the triangle that has an angle of 135 degrees with the corresponding sides of 12 meters and 20 meters, round to the nearest whole number. So I'm going to attempt to draw this triangle to the best of my abilities. Okay, so let's say that this angle here is 135 degrees, this bottom length is 20 meters, and then this length is 12 meters. We know that the area is 1/2 a times b times sine of theta. So the area is equal to 1/2 times 20 times 12 times sine of 135 degrees. Now, I'm going to use a calculator in just a moment, but before that, 135 degrees is one of our special angles because 180 degrees minus 135 degrees is 45 degrees. So that's going to end us up right here. We have a reference angle of 45 degrees there, and then we know that this angle is 135 degrees. So the coordinates for this point are going to be negative square root of 2, comma 2 over 2, comma square root of 2 over 2, like that. And we know sine is the y value, so the area is equal to 1/2 times 20 times 12 times the square root of 2 over 2. And let's see, so 1/2 times 20 is 10 times 12 times the square root of 2 over 2. And I can multiply or divide both of those. So that would simplify to 6 over 1. So that's going to be 60 times the square root of 2. Now, I think that's a lot easier to throw into my calculator. And it says to round to the nearest whole number. And I got that 60 times the square root of 2 is 84.85. So if I round that to the nearest whole number, that would be 85. And here, I didn't put the units, but 20 has meters and 12 is also meters. So our final units should be meters squared. And that is the area of this particular triangle.